So this is the formal definition of a limit. If you were to Google what is a limit, calculus, etc., you're going to come up with something either exactly like this or something really close to this. So the formal statement, if I have a function and it's defined, we say that L is a limit as x approaches c if this very specific condition is met. So give me any epsilon, that's that funny looking cursive E. So give me any epsilon that's positive. Maybe epsilon is 1 or 2 or zero point 0.1 or 1/1 millionth. Whatever epsilon I'm given, if I can find a delta, that's that weird looking O with the curve at the top of it, if I can find a positive value delta such that the distance between x and c, if that is less than delta, that makes or causes my function minus my L to have to be less than epsilon. And I should say the distance between my function and L. So if I look on my graph here, that blue C, if I can find for any epsilon, distance from L to any given epsilon, if I can find that delta that satisfies that, I would say L is my limit. Okay, so how often are we going to use this? Hardly ever. It is not on the AP exam. I'm not really going to stress this thing too much. However, it's kind of a big deal since calculus is all about limits, and this is the technical definition of what a limit is. Usually in class, we're not really going to think about this definition. We're really going to look at what I call the common sense interpretation of limits, which to me would say as x gets close to some number c from the left and from the right, so as I'm approaching that c in my x direction, what are the y values doing? Are the y values also getting really close to some number? And I need to emphasize the singular some number. It shouldn't be getting, the y values should not be getting close to two different numbers. If they are, then I do not have a limit. So the ways that we're going to find limits, one of three ways. Either graphical, meaning we just look at the graph and use what I call the pointer test from the left and right. I'll show you more about what I mean by that in class. As I'm basically just using my index fingers, are the y's approaching the same value? If so, that is my limit. If not, then I would say the limit does not exist. My second way is called numerical. This is a lot of number crunching. I would make like a table of x and y values, like we often do when we're graphing a function. And I would try to see, is there a trend? If so, that's my limit. If not, I say the limit does not exist. The most common way that we are going to see limits is algebraic. Basically, we're going to plug in that c value for x into our function. And if we don't get a problem, in other words, things like division by 0 or taking square roots of negative numbers, if we don't get one of those scenarios, then whatever we end up with is going to be our limit. Now, if we do get a problem, typically we're going to use some tricks, things like factoring, completing the square, using what I call radical conjugates. It's probably not a technically accepted across the board term, but you'll see what I mean when we work some examples in class. So really quick, let's say I'm working some graphical limits here. So I have a function, kind of a weird looking function here, and I have three different limits I'm looking for. So as I move, I don't know if my pointer is going to show up on the video there. It should though. As I'm coming from the left on my x-axis, then I'm just moving along that thing to -2. Looks like the y values of my function are starting at 4 and they're decreasing and they're going down. As I get close to -2 on the x, the y values seem like they're getting really close to -2 and the y. Now, if I come from the right, if my x's are approaching -2 from the right, my y values are also approaching -2. It just so happened that this x value that I'm approaching turned out to be my limit. That's not always going to be the case. So this would equal -2. So notice the notation here. LIM, x goes to something of my function equals that value. But I do the same thing as x goes to 1. And these two examples here actually end up being the same x value that I'm approaching. The reason why this limit is a 1, as I come from the left on the x and from the right on the x, the y values are both approaching 1. Now let's say I'm going to 8. As I go to 8 from the left, it seems like my y values, they're approaching -6. So I would say that the left-hand limit, we'll talk more about the notation and how we express that in class, but the left-hand limit, as I'm coming from the left, and approaching 8 in the x direction, my y values are -6. So the left-handed limit is -6, but then the right side, as I come from the right, as I'm approaching 8, my y values are getting really close to 3. Those are not the same. -6 is not the same as 3. So since they're not the same number, I would say D and E. The limit does not exist. Those of you who are fans of, oh, that Lindsay Lohan movie, forgetting, oh, Mean Girls. Yeah, the limit does not exist. Okay, so that is a graphical approach at finding some limits. If you want some more practice, take a second and pause the video here. See if you can figure out what those limits are going to be. And in 3, 2, 1, here are the answers to those. So you can sort of check your work there if you need to. Next, we'll take a look at a numerical approach. So a numerical approach, I'm given a limit. X is going to 0. Here's my function. I made a table of x values there. You'll notice here my x's start at -0.01 and they get smaller and smaller as they approach 0 from the left. And then I do the same thing from the right. I start with some number that's getting really, really, really close to 0. So from the left, if I plug those numbers into my graphing calculator, that's what I got when I plugged those things into this function. And then I did the same thing from the right. So let's take a look. 1.995 about, and then another 1.995, even closer, then 1.99995. So I don't know about you, but to me, it looks like these are getting closer and closer to 2. And then from the right, 2 and some change, 2 and less change, 2 and even less change. So even though at 0, if I was to plug that in, I would have division. I'd have 0 divided by 0, which is not really making any sense. That doesn't exist. Doesn't exist at 0. However, limits are all about the journey. Where are you going to? Not necessarily where you end up at. As my x's approach 0 from the left and from the right, they are definitely making the y values approach a 2. So here my limit would be 2. Lastly, here's an algebraic example. As x goes to 4. Okay, well, as we said, the algebraic approach, we just plug in the x value. If we don't get an issue like dividing by 0 or square roots of negatives, whatever we end up with is going to be our limit. Well, let's see, 16 minus 20, -4 plus 1. I think that's -3. Okay, so that's not division by 0. I'm not taking square roots of a negative, so that will be my limit. Lastly, another algebraic example here. Now, when I plug in that 2, I got a real problem in that denominator. I will have division by 0. That is no bueno. But we know from pre-calculus, turns out that that's the same as x minus 2 times x minus 4. Ooh, goody. I could actually cancel that x minus 2 factor. From pre-calculus, we should know that that would be a hole in the graph. So I still have that same notation, LIM x goes to 2, LIM x goes to 2, because I have not evaluated the limit yet. Now, if I cancel those factors, I get x minus 4. Now when I plug the 2 in, I get a -2, which is not division by 0 or a square root of a negative, so that would be my limit.